Hey guys, it's Bob Johnson, and today we're going to be looking at a balanced three-phase rectifier. As you can see, that we're looking to find our V naught across the resistor and see if that's equal to 120 volts at time equal to 0.25 seconds. And if you look here in this graph, you can see the different voltages to time at 2.5 seconds. Okay, so first thing we're going to look at here are these diodes. A diode we can basically think of as a switch in this situation. It's only going to allow current and voltage to flow one way. It's usually made out of a semiconductor like a silicon. We're going to be deciding and proving whether these diodes are in the on or off state. If they're in the off state, we draw in a circuit as an open circuit. So there's no connection. In this case, the current has to be equal to 0 and the voltage across the diode has to be less than 0 or a negative, so it's acting like an open circuit. Now if the diode is on, we would draw in the circuit as a closed circuit, and it basically acts just like a wire. Alright, so before we get started looking at these diodes, I'm going to explain a few rules to you that we're going to be using. First off is Ohm's law, which is pretty much the basics of all electronics we're going to be using. It's voltage equals current times resistance, and it works over a resistor. We're going to be using this when we're trying to find our V naught because our V naught is over a resistor. Next rule we're going to be using is Kirchhoff's voltage law, or KVL, which essentially means all the voltages around the loop will add up to equal 0. We want to verify that diode 1 is actually acting in the on position, meaning that there is a positive current across it and there is no voltage across it. What we're going to do to look at that is do a basic KVL. So we're going to go around this loop right here. As you can see, there's a 120 volts here. We're going to go around across diode number 1, across this resistor. We have our V naught back to this 120. So there's only two voltages in this. We have a 120 and a V naught. So I'm going to take this direction and I'm going to denotate this as going to the negative terminal as being a positive 120. So if I have a positive 120, I'm going to go around the loop across this V naught. Now we have to pay attention to our polarities. If I said that this is positive going to the negative terminal here, and now we're going to the positive terminal, it must be a negative V naught. So we're going to have a negative V naught. And that has to equal to 0 because those are the only two voltages shown in this loop. We're going to take Ohm's law and take our 120 across this resistor. 120 equals our IR, or our current across the resistor, times resistance, which in this case is 10 ohms. And if you manipulate that a little bit, you get IR equals 120 over 10. So the current over the resistance, over the resistor, is equal to 12 amps. The same as the current going across this diode because it is in series with each other. Current and series are always equal to each other. That's condition 1. We know that the first part of the condition is indeed true, but now we need to make sure that the second condition is true. Voltage has to equal 0. To a short, if you were to take the difference in voltage in between 2 points on this short, you would get 0 off. Diode 2. Diode 2 is pictated as an open circuit right here, an open circuit element, so it's supposed to be acting in the off position, meaning ID is 0 and VD is negative. So since it's an open circuit, you cannot have current flowing across it, so ID must be equal to 0. Now we have to solve for VD. VD2, what we're going to do is another KVL, very simple. We're going to go around this loop. I'm going to start again with a positive 120 volts and down to the negative again, so that's going to be plus VD2 as well, equal to 0. Now you subtract 120 over, VD2 equals negative 120 volts. Okay, we have both of our conditions met for diode 2. What we're going to have to do is we have to count for two voltages. Plus negative 60, then plus 120, plus VD3 equals 0. 60 volts plus VD3 equals 0. So VD3 equals negative 60 volts. So again, check. VD3 is indeed in the off position because I just know it's going to be plus 120 plus VD4 equals 0. I know that VD4 equals negative 120 volts. And again, current is 0 because it is an open circuit and current cannot cross over this open circuit. ID5. ID5, we can look at it real simply. We know it's a short, so there cannot be a voltage drop across this short. and it's also in series with ID1, so the amperage is going to be equal to 12 amps because it's in positive 120. Go across this, and now we have going into the positive terminal, so that's going to be a negative 120. So that's going to be 0 volts acting on this side of the diode. So we're going to have a double negative again here, so that's going to be positive 60 on this side. Then we're going to be, when we go to the diode, look at the voltages across that, going from positive to negative, that's a negative, so we're going to have VD6 equals negative 60 volts. So check off, that works. All of our diodes are actually acting in the state that they are depicted as. 120 minus V0 is equal to 0. Add V0 over, V0 equals 120 volts. Yes, so to answer the question, we wish to confirm the output voltage V0 is equal to 120 volts at time equal to 20.25 seconds. And the answer is yes.